So thanks for joining me today to talk about how Uber leverages JavaScript across its engineering org. It's really a pleasure to be here. So again, you probably know Uber by now. Push a button, get a ride. And Uber's mission really is to make transportation as reliable as running water everywhere for everyone. And we've done so across 6 continents in 73 countries and in more than 450 cities with more than 1.5 million drivers that on average deliver more than 5 million trips per day. And so if you'll indulge me for just a minute, let's travel back to 2009 and take a look at the first Uber app. It was pretty bare bones. You have a map, you have a button that says, pick me up. Pretty straightforward. And in 2012, we launched the second version of the app, and aside from being more sleek than the previous version, we added more functionality such as location search, ETA estimates, and the ability to select different products at the bottom. And that was 4 years ago. And then just last year, we did another refresh of the app, and now it looks like this. We added schedule rides, accelerators for known locations, and an interactive feed, just to name a few. And so now, not only can you get a ride from A to B, but you can play music with Pandora, see local recommendations with Foursquare, or even order food with Uber Eats. And it isn't just rides in cars. It's been choppers, boats. We've done deliveries from kittens to ice cream to even Christmas trees, all while experiencing hypergrowth. And so this visualization is New Year's Eve in Singapore, which is one of our most popular days of the year. And this really just shows the growth from 2013 to 2016. And so this is going to be a coming-of-age story about JavaScript and how we scaled the engineering organization. So we hired a lot of engineers. They wrote a lot of software. And when you're at a hypergrowth company like Uber, it pretty much looks like this image. We're moving super fast. Almost every week we're launching new cities, and millions of people are using our systems. We can't simply stop our systems even for a minute of maintenance. It's nearly like changing wheels on a car that's running 80 miles an hour. And so I want to set up some foundation for this because I think in order to understand the story of JavaScript, you have to understand how Uber's structured. So we're organized as programs and platforms, and the simplest way to think about it is program teams build products on top of platforms. And we're all product teams. But building a platform that interacts with the real world adds a whole nother level of complexity. Because the physical world's complexity is infinite, but we only have 64 bits and 500 milliseconds for an SLA. And unlike freemium services, Uber has only transactional users. You have riders, drivers, eaters, and now couriers. So we prioritize availability and scalability over everything else. Each person connecting to Uber is having a unique experience that's tailored around their data. And so that's led to more than 15,000 repositories that power 3,400 microservices that power 250 web apps and the 10 mobile apps that you've probably used in your day-to-day. But ultimately, Uber's ability to scale has come from high-velocity, hard engineering, along with autonomous teams and domains. And so let's talk about how we got there. So we're a polyglot engineering organization. Today, we currently have 4 languages in production: Go, Java, Node.js, and Python. And these are really listed in order of preference because we primarily use Node.js early on, but we're moving towards Go and Java on the backend services. And mainly, we only use Node.js for web applications today. But why JavaScript to begin with? It's a single stack for both the front end and the back end. It provides a simple interface and thorough documentation. When you're hiring a lot of engineers very quickly, they need to be able to get up to speed. So if you have to learn a new language, the language should be easy, and it should be documented thoroughly. And it also lends itself to fast prototyping and quick iteration. It's easy to get something usable and then iterate. It also is asynchronous, nimble, and flexible. And it avoided some concurrency challenges early on. And it has a very large ecosystem of modules and a large developer community. But again, today we only use Node.js for web applications. So why Node.js? Uber was a very early adopter of Node.js, and in fact, we prototyped the first dispatch system on Node 0.2, and we're in production with Node 0.4. And at one point, we were one of the most more money moved through the Node.js application than at any other company, up until recently when PayPal started doing transactions with Node.js. But ultimately, we chose Node.js for a few key reasons. One, it handles asynchronous I/O requests with a non-blocking single-threaded event loop. And it's particularly well suited for building distributed applications that make a lot of network requests. 2, Node.js and JavaScript in general are really excellent for quick iteration. It makes it easy to iterate quickly with a real large amount of developers. And then 3, it has a very large ecosystem. So let's talk about a few ways that Uber uses JavaScript. The first piece I'm going to talk about is our marketplace platform, which powers our core trip flow. And then our web platform, which is our global web presence, followed by visualizing our data. And then finally, we allow third parties to build on top of Uber and integrate directly with Uber with JavaScript and our Uber SDKs. But first, Uber really invests in developer productivity. Today, we have over 12,000 full-time employees, so it's really important that they're productive. So we invest heavily in teams that help them be productive. And at its core, we have our infrastructure team that's focused on compute, network storage, and all the core infrastructure pieces. And then we make it easy for developers to focus on making magic for our customers with our developer experience team. Finally, all of these microservices are abstracted through a real-time API, which is called our marketplace platform. This is what powers supply and demand, provides authentication, et cetera. And then we have standardized infrastructure for web platform, which is built on JavaScript. We have our mobile platform, and in some cases, we use JavaScript, like React Native. And then we have our developer platform, where we make it easy to integrate directly with JavaScript. But again, one of the cultural values at Uber is to let builders build. And it's really important that it's easy to build and rapidly iterate on applications. So when you want to launch a new project at Uber, you send a proposal and request comments from the entire engineering org, and then you start with scaffolding that's purpose-built around our infrastructure and around all of our internal tools. And then we make it very easy to deploy and to write playbooks to operationalize your teams. And so there's a lot of things that go into launching a new service, whether that's a web application or a backend service. So how do you manage your assets? How do you actually communicate between backend services with RPC, whether it's over HTTP or something like T-channel and Thrift? How do you manage translations? How do you manage data persistence, network compute, storage, et cetera? And so all of this is baked in by default. And one of the reasons we invest heavily in developer experience is because we want to abstract all of this away so that our developers can just focus on making magic. So let's talk about our marketplace platform. The marketplace platform, at a high level, this is what it takes to get from A to B. We have our iOS and Android Rider apps that talk to the marketplace gateway, and then the marketplace gateway abstracts away all of the microservices underneath. And so at a high level, it looks like this, but in reality, it looks a lot more like this. Because we have over 3,400 microservices that power the stack, and over 100 of those pertain to the core trip flow, just making a ride request to get from A to B. Or maybe even like this. But the real-time API is ultimately the frontline web service of Uber that most of our traffic goes to. And we have over 1,000 HTTP endpoints. But it acts as a single router to all the microservices underneath. But we have this because it provides a single place for monitoring, for documentation, and it's one interface to understand for all of our internal developers. And the marketplace was originally built on Node.js. And so some of the challenges that Marketplace tries to solve are logistics challenges, like how to minimize wait times for drivers and riders and how to maximize pickup efficiency. And if you think about Uber Pool, it's really a traveling salesman problem on steroids. And so I think Rasmus is somewhere in the audience today, but Uber ultimately started out on PHP and MySQL, like many great web companies. And that lasted about 6 months. It was originally outsourced. And then we rewrote Dispatch. And early on, we rewrote Dispatch in Node.js and using MongoDB, because I don't know if you know, but this was web scale back in the day. And at the time, that lasted for another short period of time, and we started to quickly iterate. At some point, we started to max out the ability to store all of our data in a single database, regardless of the shards. And so we had to implement our own solution on top of MySQL that we call schemaless. And then over time, we've started to break these services down to smaller and smaller components and migrate away from Node to Go into Java. And so this is an engineering timeline of how the Uber stack evolved. And so it really started as a monolith. And monoliths aren't bad. This is a pretty common pattern. Well, they're not bad at first because they optimize for developer velocity, and they consolidate the operational overhead into one place. You only have one application to deploy and one application to monitor, and if it goes down, that's the one thing you have to fix. And a monolith isn't as bad when there's a single team that owns it, but when you have thousands of engineers working globally across hundreds of teams, it quickly becomes a ball of mud. And I don't know if you know, but microservices are a thing, but a microservice is a service that is focused on only one thing. But one thing doesn't mean just one API. It means one business domain. And so when we evolved into this microservice architecture, we learned there's some pros and cons. And so the first was that there's clear ownership boundaries. Well, early on with Uber, there was a lot of autonomy, and you could choose any technology stack to solve your business problem. When you're growing at Uber's pace, you really don't want to be blocked on technology. You want people to use the tools that they're most productive with. As you scale an engineering organization, that starts to break down. And so moving to microservices allowed us to have clear ownership boundaries most of the time. It also allowed products to move at their own pace. If one team feels blocked by another team, they can implement that service and not be blocked. It allows the businesses to move faster. And it's able to solve scaling issues. Not only engineering scaling issues to make individual services horizontally scalable, but also structural issues within the company. It's the systems as well as the company. It makes it easy to just have single training, documentation, and enablement and tooling around one language, or one service rather. And it allows you to choose the best tool for the job. So it gave teams platform independence. And it also increased the reliability of the system. Because each piece is independent, makes them more horizontally scalable, each service, and then makes them testable as well. But it also increases operational complexity. When you have 3,400 services, how do you figure out which service does what? Especially when they can be named anything and the name doesn't happen to have anything to do with what the service actually does. The other problem is not all of your data is in one place, so you have eventual consistency issues. And then when you have to make hundreds of network requests underneath in order to serve one transaction, you start to run into performance problems. And because you can't have a holistic view, it becomes troublesome to find out and isolate the root cause of some of the performance problems. So distributed tracing becomes a problem. And then ultimately testing. Because there's so many components, testing starts to break down. And then again, there's operational overhead. So for every service, you need to deploy it, you need to monitor it, you need a way to commit and to have continuous integration, document, instrument, and deal with security problems. And so we learned a lot of lessons moving from monolith to this microservice architecture with Node.js. But ultimately we learned sometimes it means that there's repeated code and repeated effort. And so Martin Fowler has this great graph that shows for less complex systems, the extra baggage required to manage microservices reduces productivity. But as the complexity increases and the size of teams increase, the value of microservices increases. And so we started to invest in technology that helped us scale our Node.js applications. So all of this is open source, and at first we had a problem with sharding. So we use Google's S2 library that allows you to break a sphere down into quadrants or into regions. And so we shard based on cities, and we break the globe down into small regions that we can individually shard for those users. But then the problem is when you're building a scalable Node application that's largely distributed, you need to be able to route those requests to the right place. And so Ringpop allows us to have application level sharding and to implement it any way we want. And then once you realize that talking to many services underneath can be quite expensive over HTTP and JSON, because HTTP is really meant for browsers connecting to the server. But when it's server to server making requests, RPC is much faster. So we wrote T-channel. And so Facebook's Thrift existed at the time, but we didn't have client libraries for all the languages we want. So we invented T-channel, which is a network framing protocol that we use for RPC requests, asking for data between the backend services. And then finally, Jaeger. When you have large distributed applications, you want to be able to get visibility to figure out performance problems. And so Jaeger is a distributed transaction tracing system that makes it easy to instrument distributed applications and to figure out the root cause of performance problems. And so Ringpop looks a little bit like this. You have the client that's making a request, and you have many instances of your applications. And then for each node instance that you might be running, it's paired with a Ringpop client. And the Ringpop client simply decides that this node can either handle this request or it can forward it along. And so you can implement whatever logic you want. Ringpop is just a generic way to do application level sharding. And so either it makes the request or forwards it to the appropriate node that can handle the request. And then we have Jaeger. So this is what the Jaeger UI looks like. So this is a single request that's actually talking to about 20 backend services. And so when you're trying to figure out what's gone wrong and why there's a performance degradation, this allows you to get visibility into exactly what's going on. Observability is really key in distributed services. Logging and exception tracking isn't enough, especially at this scale. But ultimately, you should learn how to profile Node.js apps with Linux performance tools, because ultimately, Node.js is just a thin scripting layer on top of C++. So all the big boy tools just work. Things like strace, or we use Node Flame to do CPU flame graphs, which is powered by ptrace. And then these tools are really necessary for increasing the performance, but ultimately these are generic tools that work for any application running on Linux. So we learned a few lessons in scaling Node. First, early on it made it quick to iterate, but as the size of the team increased, the developer velocity starts to slow down. And microservices enforce a tight interface to have, so the problem with having many microservices is that when you change the interface, everyone has to migrate to this new design. If you add a parameter or remove a parameter or rename something, every dependency now has to make that same change. So you need a tight contract between those services. And because Node.js is dynamically typed, it means that this can quickly change. So using a statically typed language really has an impact with 100+ developers. And what we realized is that when we had hundreds of developers committing to a single code base, like our real-time API or our marketplace platform, it's better to catch those issues earlier at build time or compile time versus runtime. And again, Node.js, it's very quick to learn, but it's also very easy to write poor quality code. And when you're hiring many developers, they really are just trying to get things done, not focused on writing beautiful, performant, optimized code. And so oftentimes it enables you to move fast, but it also allows for you to be sloppy. And because JavaScript was originally written for the browser, a lot of those errors aren't caught until it's too late. How many remember the issue with NPM where a module author removed one package and took down the internet, by a show of hands? Yeah, so there's a great ecosystem of NPM modules and just JavaScript utilities, but often some of them are very immature compared to their Java or Go counterparts. And so a great example of this is the HTTP client in Node is notoriously slow. But ultimately, latency became a problem for us. Latency is too high for ultra-performant backend systems. And so what we're not talking about is the average latency. What we're talking about is the 99th percentile for the max latency. Dynamic languages that have dynamic garbage collection mean that you can't consistently forecast how performance will happen. And so when you want requests to be served in under 2 milliseconds consistently, you really need something that is reliable. And this became a problem with Node.js early on. Again, we started using Node much earlier, and some of this has changed in recent years. And oftentimes you'll need to learn it's really just a layer on top of C++, so don't be afraid of writing things that need to be performant in C++ and just exposing it to Node with bindings. But to understand how we got here, you have to understand Conway's law. Any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And so the reality is that a lot of these lessons were learned because we grew really fast, we were hiring many developers, and they were given the freedom to just get things done. And so oftentimes that means they picked whatever tools. And so sometimes we had early Node developers who attracted all of their friends and other prominent Node developers, and so we had a large knowledge base of Node. And over time we learned that we need a little bit more consistency and we need tight interfaces between all of these services. And so we learned a few other lessons along the way, which led to tools like Ringpop, tchannel, and Jaeger. First, the HTTP and JSON was designed for browsers. Using RPC is better for computer-to-computer requests. When server-to-servers are talking, you can be much more efficient by using something like tchannel and Thrift. And after a certain age, microservices become immutable, should become immutable. Again, when you have a service and there's hundreds of dependencies on that service, like authentication, for example, at some point you can't change it as much as you would like to. So it's better to replace it with a new service and ask people to migrate than it is to just change the interface. And having multiple languages allows for team preferences, but it also segregates developers based on their preferences, and it prevents the easy reuse of some code across the company. And so sometimes this can lead to issues. Early on, we tried to use monorepos because we thought that it allowed for changes to be made across multiple services atomically, but it also prevented us from open sourcing smaller components later. And then performance problems were difficult to debug in these distributed applications because we didn't have consistent dashboards and have observability tools. And then logging should never slow down production. In a failure storm, you should just drop rather than delay the requests. But the reality is that all of these are trade-offs. And everything is a trade-off. And when you're moving really fast, it's easy to let the momentum carry you. But sometimes you need to be intentional and step back and decide what makes sense for the long term. And so that's a bit about how we use Node.js on the backend applications. So now let's talk a little bit about how we use our web platform. You've probably seen Uber.com, or maybe you're interested in self-driving technology and seen the Advanced Technologies Group website, or simply signed up to take a ride or got an estimate, or maybe used our mobile application, or maybe you've been interested in some of the city data that we provide and understanding traffic patterns around cities, or maybe you were just hungry and ordered a meal, or you wanted to just have something rushed across the city. The reality is that we've built many different web applications, from Uber Central to my personal favorite, developer.uber.com, which I manage, or my team manages, and we help people build moving experiences. And so the problem with all of these websites is you need a common foundation, because as the brand changes, as the stack evolves, you really need a standardized platform. So we have a web platform team that's focused on providing this foundation, and it serves over 250 web properties today. And because without this consistent foundation, all of these applications would have been built off entirely different tools and architectures, creating a higher likelihood of security vulnerabilities, duplicated effort, technical debt, and what made the UI is not as consistent. And so if you take a look at our stack, it's primarily built off of Express, Node.js, and NPM. And on the client, we use React and Redux. And so most of this is open source. It's not particularly cutting edge today. This is a pretty standard stack. And so our Uber web platform is built off of open source. We use Nginx and Hot Proxy on the front end for our web front ends and load balancers. We use our own NPM registry internally. And then we use Babel so that we can use the latest generation of JavaScript, Express because it's a fast, unopinionated web framework, React because it solves UI components really well, Redux for state management, and then we believe in writing JavaScript, CSS and JavaScript. So one of the engineers on our team actually wrote Styletron externally, and we also use it internally. And all of these are the open source components. And then we use Gulp for standardized build tooling. But then we extended that stack. And so we had to add a couple of things to fit our use case. So we have our own internal NPM repository with built-in caching to make things more performant and to allow us to have private packages. We have our own scaffolding tool that allows developers to quickly scaffold a new project and get best practices baked in by default. And then we extend Express with customized middlewares that are purpose-built around our stack. How do you handle authentication in a standardized way? How do you prevent security vulnerabilities? How do you handle metrics, logging, analytics, internationalization, et cetera? And then we have our own Bootstrap-like UI toolkit that's built on top of React. So we have reusable UI components that any web developer can drop into an application. And then we have a new RPC library that allows us to intelligently use HTTP and T-channel to make requests to the backend services. And then all of this has shared build and test tooling to make it easy to use hot reloading, the latest versions of JavaScript, to do asset versioning, to manage deployment pipelines, logging, testing, linting, et cetera. And then finally, universal rendering, which I think is one of the biggest appeals for using JavaScript for web applications, is that you can use not only the same code on the server side and the client side, but you can also get isomorphic rendering. And then we split out our front-end and back-end components. So the idea is that the front end are those things that serve web pages from our back-end services, those that get data from some database. And services can take advantage of universal rendering and all the tooling around one JavaScript foundation. It also allows to utilize better services or better languages for implementing back-end services, and then you can scale each one of those services independently. So your front ends are separate from your back ends. And then you can also reuse the back-end service APIs for other clients. And then again, I told you that we have our own Bootstrap-like UI toolkit, and this is because we want beautiful websites with flexible components that developers don't have to implement and maintain themselves. So we have standard UI components that are really optimized for performance with encapsulated styles. But it basically gives consistent look and feel that fit our Uber brand. And so if the Uber brand changes, you don't have to update 250 websites, you can just simply upgrade your version. And then you have analytics and instrumentation baked in. So if you're using React and Redux, you can listen for state changes and simply instrument automatically for when user events happen. And we also use JavaScript for visualizing data. We invest heavily in experimental tools and frameworks because we believe in their potential to enrich our users' lives. And with things like DeckGL, we're already seeing them inform product decisions that make our experience better. And so this is a day in a life of San Francisco, and this is actually built on DeckGL. And so this is our JavaScript library that allows us to use WebGL with massive amounts of data. So map-based information is one of our biggest and richest assets at Uber, and the billions of GPS points handled by our platform every day in real time pose atypical challenges for real-time mapping visualizations in the in-browser with data-dense visualizations like this. So imagine trying to compute millions of trips and having millions of layers. So we built a set of visualization frameworks that make this easy to do, and all of these are open source. So you have React Viz, which allows you to have a React interface for building charts. React Map.gl, which provides React components for interacting with Mapbox's GL library. And then DeckGL, which provides a layered WebGL approach for dealing with data visualizations. And then LumaGL, which is an abstraction around WebGL for data visualizations. And so first is React Viz, which makes it incredibly easy to build interactive, useful charts. So they're rendering, allows you to have rendering components for visualizations like line charts, area charts, heat maps, scatter plots, sunburst, and tree maps. And so you can find out more on GitHub about React Viz. But ultimately, it allows us to implement some of these interesting visualizations so that the people who run cities can understand how those cities work. One of our other cultural values is to celebrate cities, and we understand that every city is unique. And so one of the challenges that comes with that is understanding the traffic patterns. And so we have all of this data, but that data is meaningless unless you're able to visualize it and make it easy for non-technical people to consume that knowledge. And so this is a day, so this is basically the pickups and drop-offs in New York City at any given time. And so this is just moving the mouse to see at a particular location what the pickups and drop-offs look like. And so you can see that this is very fast, 60 frames per second, with massive amounts of data. That's incredibly hard to do. And then there's this visualization that makes it easy to understand a day in the life of New York and the density for traffic over time. And so again, all of this is powered by DeckGL, and it's all open source, so people can build on top of this today. But DeckGL is designed to make visualizations of large data sets very simple by using instancing and layering. And so you can find out more at deck.gl, and you can see some of the more interesting live examples. So this is my favorite one, which shows yellow cabs versus green crab chips in Manhattan over the course of June 16th. And unfortunately, this animation's not working, but what we can see is all of Manhattan's laid out with 3D renderings of the actual buildings, as well as the traffic flow for every one of the trips. And this is all powered with DeckGL. And the same visualization for San Francisco. These are pickups and drop-offs from a known location. And then the last way we use JavaScript as an interface to our developer platform, which is our external API. And the Uber developer platform enables third parties to integrate directly with Uber to integrate their apps with the Uber experience in terms of offering ride requests, the ability to hook into the actual trips, to get webhooks and understand when requests are being made, and then to get tools about drivers and deliveries. And we provide a Node Uber package that makes it really easy to integrate on top of. And at Uber, we heavily invest in open source. So we like to give back to the community that we built so much of our software on top of. And so you can see more at uber.github.io. And so all of the tools that I've talked about today are open source. And so we have tools for the backend on Node.js at github.com/ubernode. And then we have tools for the front end at github.com/uberweb. And it's not only our code that we like to share, but we like to share our knowledge too via our engineering blog. So a lot of the learnings that I've had from here are also talked about in depth on our engineering blog. So if you'd like to find out more, feel free to check it out. But ultimately, what future will you build? Find out more at developers.uber.com. And that is all I have for you. Thank you. And so most of the credit for this talk actually comes from people much smarter than myself. If you're interested in diving into more depth, I know I only had 30 minutes today, but feel free to dive in here.
Yeah.
And that's all I have.
Thank you, Dustin. Make some noise for Dustin Whittle.
Thank you.